Okay, we are at the end of Unit 3. Make sure you have your slides out for temperature and catalyst and Maxwell Boltzmann. And let's finish up. Hey, the good news about today is it's less procedural. There's not step 1, do this, step 2, do this, step 3, do this, like there was for table inspection and mechanisms. Today's more of an overarching look at just what makes a reaction go fast. Like if I had asked you at the beginning of the unit, how do you speed up a reaction? Most of y'all usually open up with heat. Heat it up, it'll go faster, which is a good answer. The other main thing, there's other ways to speed up the rate of a reaction, but College Board is very interested in temperature changes and catalyst changes, so that'll be the majority of our focus today. Starting off with something kind of stupid. This was not necessary to write down, but I didn't tell you that. So, but anyway, just since we're going into temperature and talking about it, I just want to bring up the 3 different scales that exist. The only one that should exist is the Kelvin scale. The fact that these 2 exist is just stupid. I mean, they like go into the negatives and stuff and make you think of integers and measuring negative values. That was unnecessary because Kelvin is the true measure of temperature. All right, because temperature really just looks at kinetic energy and how much particles are moving. If particles are moving fast, it's hotter. If particles are moving slow, it's colder. But anyway, we've got these other 2 that exist. So just in a nutshell, for the Fahrenheit, for the 0 versus 100, which is what all these scales do, you've all experienced 100 Fahrenheit because you live where you live, but some of you have maybe experienced 0 Celsius, or sorry, 0 Fahrenheit, because you're able to go and travel to one of our more northern states or whatever, but it's totally survivable. When you get to the Celsius scale, though, what is 0 degrees Celsius the same as? 32 Fahrenheit, which is, it's freezing. So you've experienced 0 degrees Celsius because it does dip into freezing for a few nights out of the year for us usually. However, 100 degrees Celsius is the same as what Fahrenheit? 212. All right, so that is a much worse deal. That's like a dinosaurs are about to be extinct conditions outside. So that would be a bad deal to experience. The Kelvin scale, though, is the one that is scientifically speaking the one that we care about. You probably studied it with gas laws last year more than anything. But I just want to bring Kelvin back to your attention as we bring up temperature. Okay, so speaking of temperature, let's do that one first. I need you to know exactly what's happening when you heat up a reaction and why the reaction goes faster. A couple things about these 2 graphs that we're going to do. First off, the temperature was there, but it was small. So this one's 400 Kelvin and this one's 300 Kelvin. So add that to your notes if you missed it. All right, 400 Kelvin, 300 Kelvin. Secondly, I owe you an apology because when I brought this graph over, it cut off the top of the hump and I tried to redraw it with paint. I apparently had a seizure while I was doing it. So what's cute though is that y'all copy me so like you thought it was on purpose. So I bet when you copied the line, you tried to seizure out with me, and now you have a really stupid hump also. So that's funny. I'm sorry. But anyway, it's supposed to be a nice hump, so whatever. We'll just all suffer together. In order for us to talk about reactions happening at all, we need to introduce a new vocab word. So probably the most important vocab word of the day is activation energy. It's a very simple idea. Activation energy is the required energy to start the reaction. It's the amount of energy the reactants have to achieve to start doing what the reaction wants them to do. So maybe there's already enough energy in the system and they just use it, or maybe there's not and you have to input the energy to make them get to where they have to get for the reaction to start. On these graphs, the activation energy is being shown by a dotted line going vertical. So like on the first one, it's this dashed line right there in the middle. Over here, it's still there, but it's a lot shorter because of the temperature change that we're about to go over. I want you to notice that the activation energy is the same on both graphs. Remember, the difference between the graphs is the temperature, right? It's the same reaction, two different temperatures. Changing the temperature doesn't change the activation energy. Look, it's right below 120 and it's right below 120. So two different temperatures, same activation energy. But what changes with the hotter reaction, the first one, is that since there is more temperature, there is more kinetic energy, and the reactants are at a higher energy. So if the reactants are existing at a higher energy, there will naturally be more of them that hit the activation energy. It's a numerical value, right? Like maybe it's 1,000 kilojoules is what they have to be at. If it's a hotter system, then more of the reactants will have the required number. And that's what's happening here. Do you see how so many of the molecules at the hotter temperature hit that activation energy? But over here, where it's colder, the reactants naturally have less energy. So the majority of them at the top of this peak are sitting over here at like 75, where the required activation energy is way up here, and they're not there. It's too cold. The reaction's not happening, or definitely not very quickly. We say that we measure reactions based on collisions. If you have a lot of energy in the system, the reactants are able to run into each other more, and that's what increases the probability that the reaction will drive forward. Not only do they have to run into each other correctly, they have to be oriented correctly. Like sometimes they run into each other, but they don't react because the orientation was wrong. And we'll talk more about that later, but our whole point here is to increase the collision rate to hopefully increase the speed. That was temperature. This is catalyst, which is a different side of the coin. Do me a favor, label that both of these new graphs are the same temperature. Both of them are existing at the same temperature. Now, look at the activation energy on the first one. Do you see how the activation energy is sitting right here, right under 120? I think that's what it was on the previous slide too. This is probably the same reaction. But this time, we're not changing the temperature. This time, we're adding a catalyst. Y'all, by definition, a catalyst lowers the activation energy. That's what it does. It actually changes the activation energy. As the words say, the top is uncatalyzed while the bottom is catalyzed. And look what the dashed line does. Do you see how the dashed line is right there beneath the 120? Here, it slides back. The activation energy is dropped below 100 because we've added a catalyst, a special substance that isn't used up in the reaction. It's just a part of the reaction. Makes it go faster, lowers the activation energy. And now, do you see how the humps are the exact same? The humps are the exact same spot. They're in the exact same spot because we didn't change the temperature. The reactants have the same energy in both, but in the bottom reaction, more of them can react because since we lowered the activation energy, it lowered the number to where the reactants already were existing, so they were able to react. Now, it's my experience from teaching this that only about a quarter of y'all understand what the heck I just said for the last 10 minutes. So, what I'm going to do is I'm going to teach it all again. We're about to rewind. I'm going to start from scratch. And you have another chance to grab this because it's essential that you understand temperature versus catalyst changes and be able to compare them to each other. I'm going to do it differently this time. Don't copy that. All right. Some of you may have discovered that beneath the third slideshow on Canvas, there was one more file. It's a picture of this. So if you decide you really love what I'm about to say way more than what I said a moment ago, then go back to Canvas, click on that link below this lecture, and this image just pops up for you to look at. Let's start over. Here's a reaction happening in a beaker at 100 degrees Celsius. Those are the reactants. Do you see them? The energy of them are written in blue. So this is just the energy. I'm making up numbers, but these are the energy like in joules or kilojoules, kilojoules of the 4 different reactants that are floating around trying to react. The activation energy, the energy they have to react, is 355. How many of them can react up there? Just one. That one's at the right number, and it doesn't have to be exactly the right number. It just has to be at least that number, or any number higher. He can react. None of those can. So you know what I do? I take this beaker, and I heat it up. These are the same beaker, but this is that beaker at 175 degrees Celsius. What happens when you increase the temperature? The energy of the reactants goes up. Activation energy doesn't change. Changing temperature doesn't change activation energy. That's a really important sentence. Activation energy is not altered by temperature changes. How many of those reactants can react now? 3 of them can. Just by heating it up and increasing their energies, one of them didn't quite get there, but the other 3 did. Let's go to the other side of the brown line. Hey, this beaker is exactly the same as that beaker. I want you to verify that you see it. 100 degrees Celsius, all of the starting values are the same as what we had a moment ago. Even the activation energy is the same. The activation energy is 355. So these are blatantly identical to each other. But I'm not going to change the temperature. All right, I'm going to do the same thing. This is going to be the same beaker, but do you see how they're both at 100 degrees Celsius? I'm not going to change the temperature. So what's true about the energy of the reactants if you don't change the temperature? It doesn't change them either. Look, you see how those 4 blue numbers are the same as those 4 blue numbers? Because if you don't change the temperature, then you don't change the energy of the reactants. But I am going to change something. If I drop a catalyst into there, it becomes that. All right, so this is that with the catalyst added. And what happens when you add a catalyst? Doesn't change the temperature. It lowers the activation energy. Look what happened. The activation energy dropped to 325. The energy of the reactants are the exact same, but how many of them can react now with the catalyst? 3. 3 of them are at least at 325. Do you see the difference in the scenarios? Because they will pinpoint questions on you to make sure you understand. All right. As your slides say, there's a couple categories of catalysts that you need to know. The good news is that the vocab word that describes them is they're words that you're familiar with: heterogeneous and homogeneous. Heterogeneous catalysts lower the activation energy. They're not used up. They're catalysts. But what makes them heterogeneous is that they are in a different state of matter than the reaction that they're catalyzing. So there's going to be a phase difference between the catalyst and the reaction. For example, those of y'all that drove to school today or were given a ride, inside of vehicles, there's a very important reaction that takes place where carbon monoxide is converted into carbon dioxide and water. Carbon monoxide, super bad for us. Anyway, this reaction requires gases to collide with each other. All right, you want to increase how many times they collide so they can orient and react. But they have trouble doing it because gases are wild. They're really random, super random motion. So what I'm saying is inside the car, you might have this gas that really needs to react with this gas, all right? But they have trouble doing it. So what the manufacturer did is they put in a catalyst that's heterogeneous. If that's true, what must be true about the catalyst? If it's heterogeneous, it must not be gas, right? It has to be in a different state of matter. So it turns out that in the car, example, It's solid. Usually platinum. And what this solid strip that they put in does is it allows a area for the gases to temporarily adhere to and lets them react. As they're floating around, this gas will attach for a moment. The other gas will attach for a moment. And boom, they're making babies. They're reacting and doing the reaction that they're supposed to do because of the catalyst. It's speeding up the rate at which they can react. Different states of matter makes it heterogeneous. Does anyone know the name of the part of the car that I'm describing? Catalysts. Catalytic converter. That's why it's called that. All right, because you're converting things with a catalyst. Anyway, this is also the reason why your catalytic converters get stolen out of cars, because this strip that's usually made of platinum, it's a precious metal. Anyway, don't go rob your neighbors. Now, the flip side is homogeneous, in which case it's the same state of matter. There's lots of homogeneous ones because usually catalysts are found like in closed systems where everything is in the same state of matter. But a real good example is your biochemistry. Inside of you, you're a closed system and you're full of enzymes. The enzymes that are inside of you are mostly homogeneous. They're in the same state of matter as the reactions that they're catalyzing. But I want to remind you from your bio years that enzymes and other catalysts are highly specific. Even though they're really useful because they make reactions go faster, but they're not used up, so then they can unclick and go do it multiple times to help lots of reactions. They're very specific on the type of reaction or which reaction it is that they catalyze. The analogy that's commonly used to explain this is like a hand in glove or a key and lock example. Like if you had a glove and I was like, hey, what should we put in that glove? You just say hand, all right? Because if there was there's nothing else that fits nicely into a normal glove, right? It's only made for a hand. So it's the same with the enzymes, right? They're super specific on what reactions they fit on in order to catalyze. Or a key and a lock, right? You have a bunch of keys on a key ring and it looks like it would fit into any key slot, but it only unlocks one door. So it's highly, highly specific. Same state of matter, homogeneous. We can apply energy profiles to our temperature and catalyst changes, right? Kind of similar. We looked at this type of thing with mechanisms. But I want to remind you real quick of some thermo vocab from the very end of last school year. If you have a reaction where through the course of the reaction, the products have less energy than the reactants, see how the reactants are higher up than the products are? This is called an exothermic reaction. Because energy is being given off if the products have less energy than the reactants. On the flip side, if the reactants have more energy than the products, that would be, what's the word? Endothermic. Now, these words are not a huge deal to us right now. In January, they will be. But based on this idea and changing energy levels throughout the reaction, look at the one that I have on the projector here. Is the one that you see there endo or exothermic? Exothermic, right? Because the products are lower than the reactants, all right? The same way that you see there. So we're dealing with an exothermic reaction. But there's other energy change things that they might want you to know while analyzing one of these. One of the most important things is the activation energy. You see this first hump? That first hump is also representing the amount of energy it takes to start the reaction, which by definition is the activation energy. So if they're asking you to find that in one of these diagrams, it'll be the distance between where the reactants start and where they have to get to make the reaction start moving forward. Another common energy change that they might ask you to find is the difference in energy between the reactants and the products. All right, this will be the overall energy change, all right, from the start to the end of the reaction. But it's still the same deal, all right? You can draw the same conclusion. It's just the difference in the energy of the reactants to the products will be this other arrow that they could also ask you to analyze. Finally, and I can only find one AP exam that this was asked about, but since it happened once, I have to bring it up. A little bit of vocab. At the very top of the activation energy is where the mechanism would start. All right, those little hidden steps that it's not even showing us. But once the reaction starts, that's where you would hit your first step of the mechanism, and then you would trickle through the other steps to make the reaction take place. But there's a mechanism step up there called the activated complex. It's the first step of the mechanism, essentially, and it's the transitional molecule that gets the reaction going. So it's just layers of vocab. But again, it's just describing once you get to the peak of the activation energy, your mechanism starts. We call that the activated complex, which is the transitional molecule that makes everything start going. Ooh, thirsty. I want you to underline the word collision and orientation. Underline the word collision and orientation. I call these hot words because these are really powerful words to use if you're asked to describe the general happenings of kinetics in a reaction. All right. If you're talking about what speeds up a reaction and why, well, you can do the what, talking about temperature and catalysts and stuff. But the why needs to include collisions and orientation. Now, I've already said it a couple times today. I'm saying it one more time because it's so important. When you're driving a reaction to start taking place more often, what you're really doing is forcing the reactants to collide more often. All right. The more often they collide, the better chance that the reaction can go forward, so it'll happen faster. But it has to be at the right orientation, all right? If I take a glove and I'm like, hey, if we could put this glove on your hand, the reaction will start, and then I just throw it at you, there's very little chance that I'm going to make it land on your hand, all right? So I can make it collide with you, but in a way that didn't help us. So there's false collisions, in other words, all right? So not only do you need it to collide, you need it to collide the right way. So a lot of the collisions aren't helping the reaction drive forward. And you'll want to be able to describe this in your own words. If you were taking this course about 8 years ago, you would have to learn that reaction, or that equation down there. It's called the Arrhenius equation. You don't have to do it in here anymore, so I'm not going to make you. But it's how we get that number. If you've been sitting there maybe wondering, well, where does the activation energy number actually come from? How do we know what the value is that the reactants have to have? It's the Arrhenius equation on the slide that is funky and no longer your responsibility. I just like to show you that it exists because it's interesting to calculate activation energy. And on your lab next week, there's a bonus question in there that tries to see if you can figure out how to use it. It's optional, but you can get some lab bonus points if you want to. Any questions before we start the final stretch? I had lots of questions in all my other classes, and now I'm recording and nobody wants to be famous. So. Fine. Let's end the unit with Maxwell. He's not going to make you very happy because I confuse you right now. So lock in, right? As y'all say. There's two main things that Boltzmann went over that I want you to know. So in order to demonstrate it for you, what's the most abundant gas in the room right now? Nitrogen, yeah. So we're going to trap some nitrogen, all right? So I want you to draw two beakers. And in those beakers, I'm going to trap some nitrogen molecules. Let's trap 5 of them. All right. I'm going to make this sample exist at 300 Kelvin, and this sample exist at 200 Kelvin. All right, so they're identical beakers except for the temperature. Are you with me? Okay. Now, Boltzmann wants you to know that temperature, as I said at the very beginning, is really about the same thing as average kinetic energy. All right, kinetic energy, energy in motion. So really, temperature is supposed to be a measure of how much the molecules in a system are moving. Moving fast, hotter. Moving slow, colder. Let's label these systems A and B. Which of the systems, A or B, do you think should have a higher average kinetic energy? A is right. It's hotter, right? I just said that. So it's hotter. But here's the thing. I'm going to use arrows, lengths of arrows, to show how quick those nitrogens are moving. There's 5 nitrogens in there, right? Watch this. I'm going to say that this one is moving this fast. I'm going to say this one is moving this fast. Ooh, he's zooming, yo. I'm going to say this one's moving this fast. This one's moving this fast. Man, he's zooming his race car there. And this one's moving this fast. The lengths of the arrows is just kind of showing you comparative velocities. Let's go over to B. Now, we said that B will have lower average kinetic energy, right? So let's make him move that fast. Let's make him move that fast. Now, something happened right there, though. What's interesting about the length of that arrow? It's longer than that one. But wait a second. I said a moment ago that A should be moving faster than B, yet this molecule is moving faster than that molecule. And that's my first big point. Boltzmann says that the average kinetic energy is connected to the temperature, not the individual particle energies, which means just because overall these ones are moving faster, it doesn't mean that all of them are moving faster than all of them at any given moment. So if I finish drawing these arrows, right, they'll look however they look. But the point is, and I've tried to draw it correctly, that if you average all of B together, you will get a shorter arrow than if you average all of A together. But that doesn't mean that every arrow in B is shorter than every arrow in example A. Does that make sense? All right. Now the temperature is what is changing this. We know they're moving faster, but we just can't be absolute about per particle at all moments in time. That's point number 1. Unfortunately, He also graphed it. So let's graph it. All right. Our Maxwell-Boltzmann graph is going to plot frequency, which I'm just going to call number of molecules. No. Fine. By speed. All right. So I am going to, I'm going to make up some numbers. Who cares what the units are? I just need you to know that in my fake example, the speed is increasing on the x-axis, while the number of molecules, all right, is increasing on this axis. All right, that's made up stuff. But plotting the curve that they create will trick you. So watch. Hey, which one of these particles should have a faster curve in my Boltzmann here? A should. So let me show you what the A curve looks like. Here's the A curve. Now this will have more context when I show you the other curve. There's the A curve. Here, let's label him A. So look, for the A curve, we have a set number of molecules that's ranging about speed 5, right? Maybe 5.2, it looks like. But here's the question. What do you think the B curve looks like in comparison? What will it do to show the difference? Think about it for a second. You don't have to answer out loud. Just think, and then you'll see if you were personally right. How will the B curve differ? Here it is. Now let me explain what happened. True or false? The two beakers contain the same number of nitrogens. True. We drew it so they both contain 5. You know what that means for my graph? That means that even though I didn't draw it perfectly because we already had the seizure slide earlier, that you should have the same area beneath both curves. All right, since they're both representing 5 nitrogens, you should have the same area under that curve as that curve. So it's probably not too far off. The number of molecules is not telling you how many molecules there are. There's 5 in each. The number of molecules is telling you the number of them at different speeds. And we agree that B has more at a slower speed than A, right? Do you see it? It is showing that there are more in that container at this slower speed. And there's more at A at this higher speed, but they're present in the same amount. What if I heated up A? What if we heated them up to 400 Kelvin? What would happen to the A curve?
It would kind of like
No. Here's the new curve. Ready? It's the exact same curve because it's still the same number of molecules, right? Still 5 molecules of nitrogen. So the area underneath the blue curve and the purple curve should be the same area. But what's true about the new one? It's faster. Same number of molecules are reaching this new speed that is a faster speed because there's more energy. Takes time to get your brain wrapped around this. Maxwell-Boltzmann curves. Let's practice. Here's a question. I could ask a bunch of questions. Here's one. This is showing 4 different substances and 4 different reactions. I want to know, which of the 4 substances do you think is moving at the second slowest rate? F2. This one is. This one's the slowest. Look, most of his particles are only moving at 200 meters per second. This one is second slowest. Which one's the fastest? Helium-3. Yeah, because helium-3 crests out here at about, 1350. Helium-4 is cresting out here at about 1100. So the helium-3 is the fastest of the bunch. What do you think would happen to the F2 curve if I were to cool down his reaction? What would the curve physically do if I cooled it off? It would shift which direction? It would just shift left. Same curve, but if you change the temperature, it would just simply shift it left to show that the same number of molecules slowed down. All right, I'd like to end with a mind-blowing thing that won't be on your test. Just like to give you some frame of reference. You know these nitrogen molecules that are floating around the room right now? How fast do you think they're moving in miles per hour? Throw a number out there. I'll tell you to go higher or lower. How fast are they literally moving right now in miles per hour? What do you think? Go higher than 27. Go higher than 200. Go lower than 1,000. Higher than 800. Higher than 850. What? Lower than 975. Lower than 950. We're having fun, aren't we? Higher than 925. Higher than 937. Ooh, lower than 945. They're moving at 944 miles per hour. Y'all, that should blow your mind for a few reasons. Now, we're lucky that they're so small and insignificant in regards to us that they don't just kill us by hitting us that fast. But another interesting thing is that the speed of sound is slower than that. So the nitrogen molecules are moving around the room faster than the sound waves that you're hearing right now. Like, we don't have any use for this knowledge. I just like to throw this at you so that you can leave with fun trivia. But that's a mind-blowingly fast speed. Yes?